I'll just read a quick introduction and then I'll turn the floor over to our speaker. So hey everyone, welcome back to the Protocol Labs Research Seminar Series. It's great to have you. Our speaker today is Dr. Rohin Shah. Dr. Shah works as a research scientist on the technical AGI safety team at DeepMind. He completed his PhD at the Center for Human Compatible AI at UC Berkeley, where he worked on building AI systems that can learn to assist a human user, even if they don't initially know what the user wants. He's particularly interested in big picture questions about artificial intelligence. What techniques will we use to build human-level AI systems? How will their deployment affect the world? What can we do to make this deployment go better? He writes up summaries and thoughts about recent work tackling these questions in the Alignment newsletter, which I will be sure to link in the video description. Dr. Shah, I will let you take it from here. Thanks for coming to speak.
Cool. Thanks so much for introducing me. So this is going to be a pretty informal talk. I am going to be assuming that people have at least some amount of background knowledge of AI alignment. And I know that, I'm sure, and probably some of you have seen the talk I gave at EA Global, but I'm sure some of you haven't. That's probably fine. You might get lost at some parts, but I think mostly it should all make sense. And if it doesn't, feel free to interrupt me. I think it is always hard for me to calibrate talks, so I'm much more interested in spending a bunch of time on a single slide and being like, all right, let's make sure that we understand the things on this slide, and ignoring the rest of the talk. It's kind of useless to give a talk that nobody can understand. So let's just get straight into it. So I'm going to say the word AGI a bunch during this talk. I don't really want to, I don't like the term very much. It's just I don't really have a better term. I don't necessarily mean that it's a single monolithic agent. I don't necessarily mean that it's, like a god that's able to do whatever it wants. Just, this is a powerful AI system of some sort. And, I'm not trying, I don't have particular claims about how powerful it is, what the level is. I'm going to be vague about it, and I'm going to try to say things that make sense despite the vagueness. Cool. So a bunch of you, as I mentioned, probably have seen my EA Global talk, so you'll probably recognize this slide. So what I'm going to be focusing on in this talk is this area over here. And roughly the thing that unifies everything in that area is that it's about problems that can occur via your AI system actually quote unquote trying to hurt you. So, things I'm not going to talk about. I'm not going to talk about the impacts of AI. So I believe Andrew Critch is going to be speaking next week. He will probably tell you about sort of how multi-agent interactions that are enhanced by AI systems can lead to sort of what we might call an ascended economy in which lots and lots of things are being produced, but humans just aren't a part of that economy, and that as a result we die out. Might be I have lots of thoughts about that, but it seems like a thing you might want to be concerned about. I'm not going to be talking about it. It's not a case where the AI system is just sort of maybe as a subpart, some of the AI systems are trying to do things that they know are not what humans want. But the core mechanic there of economic competition causing us to set human values aside and instead pursue the production of things. That mechanic is not particularly AI specific and not about an AI system that is trying to hurt you, or trying to do things that are not the things that you want. similarly, things like, we fail at figuring out what it is we want as humans. Like, we fail to figure out what our values are, and so we like don't colonize the stars and make the world, make the universe as best as it can be. Depending on how exactly that comes out, I might be like, yep, that's not a failure of the sort of problem I'm thinking about. It might be plausible that that happens, but it's just not what I'm talking about here. Yeah, cool. So yeah, assumption number one, we're talking about failures in which an AI system is sort of deliberately trying to do something that it knows humans don't want. Okay. So I really like this notion of a threat model, which is a combination of a development model that says how we get AGI and a risk model that says how the AGI system then like causes an existential catastrophe. And so like, a typical story might be like, all right, we're going to do some like gradient descent on training data. This is just sort of standard machine learning, and this is going to, create an AGI that's implemented as a neural network. And then this AGI system is going to like, do some social manipulation or persuasion, or something like that in order to get a bunch of people to like fight with each other. And then eventually this like leads to a bunch of nukes being deployed, and then we all die. Like, that's a kind of story you might want to tell. There are like lots of problems with that story. I don't actually like endorse the story the way I said it, but like something along those lines. So here, the development model is this part, which tells you how we get from today to, and then there was an AGI. And then the other side is the risk model, which tells you how you get from the AGI to existential catastrophe. And the the reason I like this model is that it emphasizes that these two stories need to overlap. There has to be a single notion of AGI that works with both of them in order for you to credibly say like, yes, this is the way that we could actually get to an existential catastrophe. And I think that's something I want to emphasize as an important thing that any AI safety researcher should be doing as part of their research. Yeah. So specifically, the three claims I'm going to make about threat models is that one is like, you need to have a development model if you want to be developing solutions that actually apply to real systems. Like, if you use a model of AGI that is just not actually the one that we build in the real world, well, then your solutions are most likely going to be useless and never deployed. So that would be, you need to be working in the right development model. Two is that risk models are important for finding solutions. This one is sort of like a little less obviously true. You could, in principle, be like, rather than think about plausible risks, I'm just going to like try to come up with an algorithm that sort of guarantees safety. You can like prove a theorem that says this AI system will be beneficial for humanity. And then you don't really have to think about any risks because you've made a positive argument for safety rather than trying to avert a bunch of negative arguments for risks. I mostly am just going to claim as an empirical matter that it seems real hard to do this kind of positive argument without having come up with some risk models. I'm especially skeptical of being able to prove a theorem of the form this AI system is beneficial for humanity without a bunch of strong assumptions, in which case then you have to doubt all of the assumptions. So I'm making an empirical claim that in practice, you're probably not going to get very far without risk models. And then third claim, which I already argued for a bit, is that we should be using the same notion of AGI for these two models. So what threat models might we have? So a common one is a sort of utility maximizer threat model. And I'm going to present a sort of simplified view of it. It's almost certainly not going to capture the diversity of viewpoints that exist in AI safety. So, don't take this as a representation of people who work with utility functions. But anyway, so in my version of this model, let's say, you could, what your AGI system is it's sort of like, there's this algorithm or brain or something that's able to do a lot of reasoning and planning and logic and stuff and learning and stuff like that. And there's, somewhere in there is this utility function that you can slot in. And then once you slot in this utility function, out comes plans that for achieving high utility according to that utility function. And so if you take this as your AGI model, then there's a good risk model for this, which is basically if you've got this sort of AI system that is pursuing a goal or utility function, then it seems like there are a lot of convergent instrumental subgoals that such a system would be incentivized to try to achieve. So for example, whatever your goal is, it's really a good idea to stay alive so that you can actually finish, complete the goal. This doesn't require you to have survival as an intrinsic goal. It's just, any plan that maximizes your chance of achieving your goal will probably include, if there are significant risks to your survival, that plan should include actions to mitigate those risks. And some of those risks might be the humans try to shut me down. And so you take actions that mitigate the risk of humans shutting you down. Similarly, if you gain power or gain a bunch of resources, if you have a lot of money, then you have your scope of action is a lot broader. And so that also seems very useful for achieving your goals, almost no matter what they are. And sort of the pursuit of all of these instrumental subgoals seems not great for humans. So it's a pretty good risk model. The question is sort of what development model really corresponds to this? Do we have one? So one thing people will say is it just sort of seems like in order for a system to be useful, it needs to be of this form. It needs to be doing this sort of planning, learning, and so on. You can't really be useful without that. And that's sort of their justification for this one. I personally feel a bit skeptical of that argument. It feels like I sort of agree that in normal situations, yeah, you're going to need to acquire resources and learn and things like that, but it's not obvious that this will then sort of lead all the way to causing extinction. But it seems plausible. I sort of feel pretty confused about that, really. People's opinions vary. Some people are pretty confident that does work, that argument does work. Then there's a more concrete development model, which says what we're going to do is we're going to have a researcher just going to develop a bunch of algorithms for doing this sort of planning and search and causal reasoning and logic and hierarchy and all this sort of stuff. And maybe we'll use deep learning to do vision. We'll get a screen of pixels from a camera, and then we'll throw deep learning on top of it to turn it into things like cats and dogs and chairs and people and stuff like that. But the actual intuitively the actual agentic parts, the parts where the agent is doing plans in the world, will be these more explicit algorithms that have embedded into them a criterion by which you evaluate different plans, which is what this utility function is. So that's so that's a utility maximizer threat model that you could have. And with this sort of threat model, in the section of things that I said I was talking about, that sort of corresponds to this area of the graph. So if you're familiar with Mesa optimization, the reason that's not in here is that Mesa optimization is fundamentally like, if you select for an agent that gets good outcomes, you might get an agent that gets the good outcomes for the wrong reasons. But it's like fundamentally an argument about selection pressures and outer optimization. Whereas sort of in this previous development model, like maybe it applies, maybe it doesn't apply, it's not totally clear. But like one reason you might think it doesn't apply is because it's not that you aren't selecting the agent for good outcomes. You are explicitly like putting in the criterion of rightness into the agent and then designing an algorithm that takes that criterion of rightness and uses that to form plans. So there's not really a chance for there to be this sort of divergence between what you selected the agent for and what it actually does. So, it's unclear whether or not Mesa optimization can apply. I think there are also arguments for it applying, but it's definitely less clear than in the canonical case. On the other hand, things like, did you specify the right reward function, the right utility function? Clearly, obviously a problem in this sort of scenario. The entire point is like, if you get the utility function wrong, then your AI system pursues convergent instrumental subgoals and like then ends up killing you or causing some sort of existential catastrophe. And so that can be fixed by like tackling the specification problem. And so techniques that do this are like assistance games, learning from human feedback, tent alignment, stuff like that. Informed oversight is, well, maybe I won't go into that. The reason I don't have scaling to superhuman in there is like mostly because the specific methods that people have proposed are very learning focused, and it's not clear how you would translate them into this other regime. But I do think that like in general, figuring out how you scale to superhuman performance is like a thing you would want to be thinking about in this paradigm as well. Cool. Any questions on that?
I would love a little clarification on what you mean by convergence of subgoals.
Yeah. So it's maybe not the greatest term. It's just the one that is commonly used, but like one of my collaborators prefers robustly instrumental subgoals, meaning that like sort of robustly, regardless of what the utility function is, these are useful instrumental subgoals that the agent will probably pursue. Does that answer the question?
Yeah, thank you. I also had a second question of in the specific example of like the politician wanting to give a tailored message to every potential voter. Like I feel like this becomes a clear utility maximizer, and like you could imagine this being quite possible with slightly better engineering and not much better modeling, really. Do you see this as like a possible, like it? I don't think it has to be an AGI to see that threat, but do you think that there are useful alignment mechanisms that we could use to fight that kind of like an artificial narrow intelligence trying to do that?
Yeah, it's a good question. I would say that the primary issue in that case is that the politician wants the AI system to be doing that. So I would say it's not a failure of AI alignment in the sense that I am using the term here. because the AI system is doing exactly what its designer intended it to do. That being so, like my usual stance on this sort of thing is like, yeah, the way we want to fix these sorts of problems is like via the sort of typical mechanisms we use to solve, as Carola, I don't know how to pronounce it, sorry, suggest human-human alignment problems, things like, laws, regulations, social pressure, stuff like that. And like, you might worry that like, the politicians get boosted by AI, but then like maybe the regulators or lawmakers or like ordinary citizens also get boosted by AI. Maybe you give everyone their own little AI system that tells them when they're being manipulated by politicians. So yeah, I don't.
Yeah, that answers.
Great.
Thank you.
Yeah, I am not going to like say that any one of those will work, but that's sort of broad category of solutions. Cool. Onwards. There is a deep learning threat model, which you might have expected given that I work at DeepMind. So in this case, your AGI is implemented as just a neural net, and the neural net itself is the thing that is it is the AGI. It's not the process of gradient descent or anything like that. It's like the neural net with like already trained parameters is an AGI. This would be something like GPT-3, for example, is like maybe the sort of thing to have in mind. You like give it an example and input, and it like you give it like a sentence, and it's like able to understand that sentence or learn from that sentence and like do something sensible on the other side. Except with an AGI, it would be much more powerful. And so then the development model is basically, it's sort of, this one's very broad. There's definitely a lot of detail to go into that I won't go into, but it's something like, either we use something like DeepRL, so that's like AlphaGo and OpenAI 5, which were both trained with DeepRL and then like learn very good policies, or you do something like GPT-3, where you like train a neural net just to predict the next word in a giant data set of human sentences, English sentences. And because this neural net is trained on such a diversity of data, the only way that it can like actually do well on this is to learn some form of general reasoning, quote unquote. And that's what then ends up making it an AGI. Again, super hand-wavy and vague, mostly because it's not the focus of this talk, but that's roughly the development model I have in mind. And so then you might ask, what is the risk model here? And there are really two risk models. Before that, I should mention I'm going to be making the assumption that we're going to have the AI systems that are asking that we ask to perform specific tasks rather than sort of generically optimizing for human values. So like one example would be this sort of like conversational agent, which is like helping you with calendar scheduling. So here we have our agent, and maybe Bob asks his agent something like, I want to hang out with Alice. And the agent has a model of like, Bob likes to go to clubs. Bob prefers to, have social events on the weekends and the evenings, something like that. Maybe the agent talks to Alice's scheduling agent, and they like figure out a time when both their schedules are mutually compatible and so on. And eventually, they schedule an event. So I'm sort of imagining AI systems that are like that, and not AI systems that, figure out the like, true meaning of humanity's existence and then like try to make that a reality. Like maybe we build those sorts of AIs in the future. I think the sort of risky AIs happen a lot sooner than that. And so I'm more interested in like dealing with the like first risky AIs and then like using those first risky AIs to help us with future AIs if we decide to build them. Yes. So back to risk models for the deep learning case. The first one is that you have a bad reward function or loss function that you train your AI system on. And so that would be this area of the graph. It's sort of basically the same thing as in the utility maximizer case. For sort of obvious reasons, reward functions are very similar to utility functions. And so many of the same things apply. This time you'll notice that the scaling to superhuman block is inside of the area, and that's mostly because the approaches in there are learning based and do apply to deep learning. So I don't really have too much to say about that. I think one critique you could have about this though is like, in some sense, it's a little odd for this to be going wrong, because like presumably humans and or companies, when they're training their AI systems, are going to be looking at what those AI systems do. And if the AI systems are doing things that are bad or incomprehensible, maybe they just don't deploy those AI systems or train them not to do that sort of stuff. And it's a whole complicated debate. But there's I guess there's sort of like controversy there is maybe what I'll point at. I won't make any strong statements. But I'm going to mostly not focus on this one, and instead just sort of assume this distributional shift problem. So the first part of this assumption, which is uncontroversial, is that there's going to be a difference between the situations that an AI system is trained for and the ones that it encounters after deployment. And I'm taking a very broad notion of distributional shift here. So like if the AI system learns a new fact, or like thinks a bit longer and realizes some logical implication of the facts that it already knows, or like the world outside a pandemic hits, those all count as distributional shifts. So it is a pretty broad notion. So the fact of it occurring at all is not very controversial. The assumption I'm going to make that is controversial is that handling this difference is sort of the hard part of AI alignment, where by hard part I might mean something like, I don't know, 95% of the risks of AI alignment, which I'll remind you is when the AI system is like specifically trying to do something that isn't what humans want. 95% of that, the existential risk from that is like coming from the AI system being okay on the training distribution, but then like becoming worse as distributional shift happens. Do I want to argue for this? I guess one thing I mostly won't argue for this. The one thing I'll note is like typical treacherous turn arguments where like the AI system sort of plays nice until it has enough power to then take over the world, do sort of count on my view as a distributional shift case, because during training it was not powerful and had to play nice, and then like only after deployment did it become powerful enough to actually take over the world. If it took over the world during training, then that's then like this assumption was false. And I have reasons for expecting that won't happen, but I'm not going to get into them. Anyway, this is just an assumption for this talk. So the example to have in mind, I think, whenever I'm talking about this, we've got our scheduling assistant. This is just a copy of what was on the previous slide. So it was, trained this way, and then, at deployment, turns out a pandemic hit. Sad. And then, when Bob says, I want to hang out with Alice, he, presumably means I want to have a video call with Alice. or something like that. And like the agent might even know this, that Bob means that he wants to do a video call. But like, the agent was trained that like when Bob or when its user asks to, hang out, that just is, the thing that it's supposed to do is to like schedule a night out at a club. And so it just continues to do that. And this is not an existential risk, but it is sort of it's a case where it's easy to wrap your mind around about how exactly distributional shift can like cause bad outcomes. All right, so that brings me to the second risk model for deep learning, which is bad generalization, which roughly means like, well, I mean, it's just sort of obvious, I guess. Your AI system performed well, by which I mean like got the right outcomes in the training distribution, but then when you move to a test distribution, it like stopped doing that, and instead did something that caused an existential catastrophe. And so like the treacherous turn is sort of an instance of this, where your model was always deceiving you, but in the training situation, it still, did the right things. It caused good outcomes, and was, despite, doing it for the wrong reasons. And it was only after the distribution shift that it like generalized poorly, and then, caused humans to die. And so this, I would say, is more this category of things. I will come back to why it is this category of things at the end of the talk, but just wanted to signpost that for now. Before we get to sort of solutions for this risk model, I want to like argue for how you should be thinking about this risk model. And the way I've phrased this claim is like, we should be trying to produce generalization guarantees and not utility functions. This is, conditional on the assumption that distributional shift is like the hard part of AI alignment. It's like 95% of the risk or something like that. So, and I should note, I'm not claiming that utility functions are useless or something. And, it's still important for this goal to like train your AI system on the right thing. So, it's still instrumentally useful to work with utility functions. I'm trying to say like, when you're thinking about, in this risk model, when you're thinking about how is my solution helpful, you should be thinking like, how does it help us to get closer towards a generalization guarantee, rather than how does this ensure that we have gotten the right utility function to like plug into our AI system. I was supposed to, oh no, that's in the future. Sorry, forgot that I made a change to my slides. So yeah, so what do I mean by generalization guarantees? It's pretty straightforward. You want to produce basically two guarantees. One is that you get strong performance during training. Like when Bob asks, hey, I want to hang out with Alice, the agent, actually schedules the calendar event. You might think of this as like sort of like the capabilities guarantee, that like, your agent is actually useful in the situations that it was meant to be useful on. And then the second guarantee, which is more like the safety guarantee, is like acceptable generalization. So you're not required to do exactly the right thing in the deployment setting. Like, the world could be wildly different, and then you just don't know what's going on. But, you should never be doing things that are known to be bad or something like that. You should never be trying to do things that humans would not want. And so then when Bob says, I want to hang out with Alice, maybe the agent says, like, what should I do about COVID-19? Or maybe it just knows that actually what Bob wants is a video call, and then it schedules a video call or something along those lines. The point is, like, you have some sort of acceptable generalization. And like one of the research questions is like, what should we define acceptable as? Yeah. So generalization guarantees, I think, fairly straightforward. So to contrast that, the contrast to that was utility functions. For utility functions, in this talk, when I say utility functions, I just mean, utility functions, reward functions, goals, objectives, all the same thing. There are definitely many concepts that these things can point to. And some of you might be like, oh, but a utility function is X, whereas a reward function is Y. I'm like, yep, that seems plausible. I'm going to just sort of like use the same word or use all of these as synonyms and then try to more precisely identify the more precise concepts and then talk about each of those concepts individually without trying to use the baggage of a specific word. So I'll just go through all of these concepts and then like say why they don't seem to me to be good goals for alignment in the world where the thing that where we think that most of the risk comes from distribution shift. Cool. So the first kind are behavioral utility functions. So this is pretty straightforward. You take your agent and you take its training data that it was trained on. You look at how the agent behaves on that training data. And then you say that, the agent's utility function is this function U that basically rationalizes or explains the agent's actions on this training data. And sort of the biggest problem with this is just that there are many utility functions that are consistent with this training data, and there's no way to choose amongst them. So like in our scheduling assistant example, like you could have the utility function that is where the agent is like, doing whatever Bob wants it to do, at least when it knows what Bob wants it to do. That's consistent with the training data. But there's another thing that's consistent with the training data, which is, in like situations where Bob asks to hang out with a friend, I get high utility for scheduling a night out at the club. In situations where Bob asks to schedule a work meeting, I get high utility for scheduling something between the hours of 9 and 5, and so on. And like that's a utility function that's also consistent with the data. And in my hypothetical example, that one was the quote unquote correct one, but you can't tell just from the training data. So an equivalent way of saying this is like if you do choose a utility function from using this method, you don't really have any reason to expect that it predicts correctly outside of the training data. So yeah, so obvious fix, get rid of the training data. Just find a utility function that works in all possible situations. So now you say, for every input. So on the previous slide, it was for all inputs in D, where D was the training distribution. Now it's just for all inputs. The agent's behavior on that input needs to be explained by the utility function. This one has a bunch of problems with it. One is like, it's kind of hard to apply this to humans. I don't know, man. I'm giving a talk right now. I could have several goals in getting the talk, but I don't think you could reasonably make a case that there is some like overall meaning of life type goal such that both this talk and, random like playing Minecraft, which is a thing I sometimes do, are both, contributing to this life goal. It sort of feels like this is not really a very crisp concept that's going to work with humans. And so like, I don't know why we should expect it to apply to AI in a nice way. You could obviously have the utility function that's just like, at 10 a.m. on whatever date it is today, April 13th, 2021, Rohin will get high utility if he gives a talk to protocol labs. And like, that's a thing that, that's a utility function that does rationalize my behavior, but like all behavior is rationalizable in this way. It's like sort of degenerate. You don't really get anything out of this. So yeah, if you aren't doing something like correcting for biases or mistakes, if you're just like literally taking this equation as written, it's just a new encoding of the policy. It's the same thing as like just expressing the policy. So you haven't really gained anything. You could try to be like, okay, well, we know we can like try kind of sort of like figure out what biases people have, what mistakes they're making. We could try to do the same for the AI system, correct for that. And then after correcting for that, we might get an objective that says more things. But like, I don't know, man, it seems real hard to like say what exactly counts as a bias versus a mistake versus like just an unusual preference. I think this is true for humans too, but it seems like it'll be even way more true for AI systems. At least with humans, you get to like, we have similar cognitive architectures. While the typical mind fallacy is a thing, it's like still like mostly true that we have typical minds relative to each other. Like my mind is like way more similar to your mind than it will be to like an AI's mind. So like we, with humans, we have like a lot more ability to correct for biases than we should expect to have for AI systems. So it's a challenge. And finally, like you're sort of like requiring your utility function to explain the agent's behavior on all possible inputs. So like computing this utility function would require you to know the agent's behavior on all possible inputs. But if you know the agent's behavior on all possible inputs, then like you already know whether or not it's safe. It's like, did that lead to X risk or not? Yeah. In some sense, this is just a restatement of the second point, is like, because it's mostly just an encoding of a policy, you don't learn much more. And so it's not very helpful for AI alignment. So yeah, so those are two behavioral utility types of behavioral utility functions. The next type of utility functions we can try are structural utility functions. So structural utility functions are ones that, rather than looking at the behavior of the AI system, they more look at some like internal property of the AI system or of the training procedure for the AI system and identify that as the utility function. So this is probably the more canonical sense that you would expect. You would have like seen the term utility function in. So for example, an outer structural utility function is just sort of the reward used to train the agent. So if we go back to our DeepRL setting, here's, Dota, and here's a reward function for Dota where you just get +1 if you win, -1 if you lose. And, it's just a typical RL setup where you like the agent sends actions and the environment sends back observations and rewards. And in this case, you would identify this, reward function as the outer structural utility function. Yeah, so it's just the reward used to train the agent. And like, I think this is an important thing to get right. But since we're talking specifically about, problems that arise from distributional shift, I think this is not the thing you want. This is not the concept you want to be using for those kinds of problems. And the reason is pretty simple. It's just that the agent, the values of the weights in the parameter in the neural network, those are completely determined by the values of the reward function on the training data, right? Those are the things that you use to compute gradients. The gradients are the things that modify the weights. The weights are never modified by anything else. There's also things like initialization and architecture and stuff like that. But those are independent of the reward function. So like the only way for reward information to flow into the agent is via the values of the reward function on the training signal, on the training data. So like, who cares what the values of the reward function on the test data is, on the deployment data is? It doesn't matter. It's not going to affect the agent. there's like, sometimes you'll like think of things like, online training or monitoring where you like also evaluate the reward function at deployment time too. And in that case, you want to make sure that the reward function works in whatever situations do come up in at that time. But still, you don't need it to be literally like, all possible situations. And yeah, you like, yeah, for the case of things like treacherous turns, where like the problem is there's a distribution shift, and then there's some like qualitatively new situation that the agent does something bad on, like it doesn't matter if your reward function had a high number, had like, penalized that situation if that situation never came up during a time when you were computing gradients. Another problem is that like, this is much more minor, but it's often unclear what does and doesn't count as part of this. So like, I think my canonical example here is exploration in DeepRL. So you can get exploration in DeepRL in a variety of ways. So one common way is to add a term to the reward function or loss function that rewards the agent for visiting new states, or like visiting states in which it like can't predict what's going to happen or something along these lines. And that's one way you can get the agent to explore more. And presumably that seems like it should be part of the outer structural utility function, because it was a term added to the reward function. On the other hand, you could also incentivize exploration by like changing the action selection mechanism such that when it's saying I'm going to like take the action that maximizes Q value, or you instead do like not the one that maximizes Q value, but instead the one that maximizes Q value plus some term that like some term that quantifies like how uncertain the agent is about the next state. Like maybe you have an ensemble of dynamics models that are trying to predict what the next state will be, and then you take their disagreement as a signal of uncertainty. And that one is part of the action selection mechanism rather than part of the reward function. So it seems like it shouldn't be part of the outer structural utility function. But both these methods are like incentivizing exploration. They probably have pretty similar effects on the agent. It seems kind of weird that one of them is part of the outer structural utility function and the other one isn't. All right, so we were like, I argued against identifying something in the training process as the utility function. So maybe instead what you want to do is you want to identify something internal to the agent as the utility function, which has the benefit that like it does in fact continue mattering even at deployment time, because you are still running that part of the agent at deployment time, whereas you aren't running the training process at deployment time. So these sorts of definitions are usually going to require something along the lines of like an assumption that the agent implements a search or planning algorithm. And then so you're like, this particular part of the network, probably all of it is, some sort of planning algorithm that's, considering different possible plans and then rating them according to some metric of goodness, and then executing the one that has that scores highest on that metric. And so then you just sort of look inside the neural net and identify the place that is that metric of goodness, and you call that your utility function U. So it's the goal that the agent is pursuing. If you're familiar with Mesa optimization, this is what you would call the Mesa objective. And the problems with this one is mostly that like if you interpret, thank you. If you interpret the assumption like strictly, where you're like, no, this is actually a planning algorithm. It really does, like, you can see the like 4 plans. If you could only understand the activations, you would see 4 plans and see them being, rated by this metric of goodness and then being compared. Like, if you interpret the assumption very strictly in that way, then I just don't think it's true. This just does not seem to be likely to be true of neural networks. And if you interpret it loosely, where you're just sort of like, it's going to be sort of like a planning algorithm, there'll be like, it will sort of look like it's optimizing for some specific objective, and then like maybe if you like understood the algorithm well, you could like tell some story about why it's going to be like generally selecting for the actions that have high values of this metric for goodness. Then it just sort of feels very vague, and like I'm not sure that I'd believe it or something. But also I think you'd have the you'd have similar problems as with the behavioral utility functions, where you could have like many possible interstructural utility functions that make different predictions. And I think that is a good point to stop, given that I am very close to the hour. I have a little bit more, which I can talk about afterwards, which is more about solutions. It's like 1 or 2 slides, but let's start with questions for now.
So mine's a bit of an odd question. I noticed that you at one point said that this particular alignment tool is hard to apply to humans, and so it seems like it'd be at least as hard to apply to AIs. And I was curious how common it is to think about applying AI alignment tools to people or things like that. I kind of independently came to this idea that if you want a company to have some nuanced mission, you should really do something like value learning with every employee, saying like, here are 2 things the company could do. We would value this one more, and just give people a lot of training data so that everyone eventually agrees on some like implicit value system, so that you can avoid the whole company turning into some shareholder value maximizer, which I think that large companies that are particularly bad at onboarding people culturally, or bad at expressing the deep-seated philosophical values of the company tend to wind up in. And I'm curious if this is something that you've seen in other places, or like has come up in a lot of do people come to you with questions around like corporate alignment to use AI alignment tools for that?
Yeah. So no, people don't do that to start with. But on the broader question, I would make a distinction between like concepts for alignment and like solutions or algorithms for alignment. And I like pretty strongly want concepts for alignment to apply to humans too. Like my best guess, at least in the neural net paradigm, I think I am less tied to that in the like utility maximizer by known algorithms paradigm. But in the neural, I don't know, they're like, it sort of seems like the way neural nets are made is like kind of similar to like how evolution made humans, or even how human brain learning works. So like if a concept doesn't work for humans, then I need some like a really good argument to believe that it's going to work for AI systems. The fact that the concept works for humans doesn't mean that it works for AI systems, as with biases. I think cognitive biases is like pretty sane for humans, but may not be for AI systems. But it feels like a necessary condition that the concept should apply to humans too. Then on solutions or algorithms, people do in fact think a decent amount about how to apply these sorts of algorithms to humans, but it's not always a thing that you can do. There are just a lot more affordances we have with AI systems that we don't have with humans. So like interpretability is a good example, where you can just read off the literal activations and weights of a neural net. Like they're not super understandable, but at least you have access to them. Can't do that with human brains. It's kind of rough. And then there's if you're familiar with AI safety via debate, one of the tools in there is cross-examination, which is when your AI system is like conducting a debate. Sorry. Our dog is very bark happy. But so yeah, AI safety via debate, cross-examination, when you when a debater is like sort of making some sort of argument, you, before they make the argument and see counter arguments, you like save a copy of them. And then after you've had the argument, you can be like, I think you're just using this concept in different ways. And like if I had said something else, you would have like used it. You would have used a different interpretation of that concept. And then you can just take the saved one and be like, what do you mean by this concept? And they have to answer without knowing how the rest of the debate played out. And that's obviously not a thing you can do with humans. So yeah, so you don't always get to apply alignment tools to humans as well, but when you can, it can be quite nice. Oh, the other thing is like you get to do like millions of examples with AI systems, and you can't do that with humans.
Yeah, interesting. Thank you.
Okay, it seems like one of the like central ideas here that you're thinking about is distributional shift. And I'm wondering if you think of that as something, as the kind of thing that we can like simulate, and is the question just like generating the right synthetic data, or is it like something weirder, and is it going to be like harder to solve?
I don't think it is as simple as just doing the right synthetic data. So like, for example, it's hard to say how you like generate the right synthetic data for like the AI system is like more powerful than humanity and could take over the world if it wanted. Like, if that's not true, the AI system might pick up on that, which presumably, and if it is true, then the AI system might actually just take over the world and kill us all. So there definitely does seem to be some amount of like, it's not as simple as it, or like, even if we magically did know the deployment distribution, which I think is like too strong of a requirement, we're not going to be able to do that. Like, it requires you to like predict COVID-19 in advance, for example. And just like, the like billion other things that could have happened that would have been like, that were as similar-ish to COVID-19. That's already hard. But then even if you could somehow do that, I feel like the like agent becoming more powerful than humanity one in particular feels quite hard. On the chat, pre-registering terms is a good technique, but the debate one is actually quite a lot more powerful because you can do the pre-registration after seeing how the debate plays out, which can actually be quite powerful. Like, I don't know if like, often people will like look at how forecasting questions resolve and then be like, man, I wish I had pre-registered such and such term, but I just didn't think about it beforehand. If you've saved a copy of the other debater, you can do that. I might want to present one more slide. So just wanted to come back to this thing that I signposted a long time ago. Sort of in the sort of bad generalization risk model. So I sort of talked about why we don't really want to think about utility functions and instead want to think about what generalization guarantees we can make. And so like, one thing that you could try to do is have your models get the right answers for the right reasons, not just get the right answers, which is sort of the default. And things like informed oversight and iterated amplification and debate are like trying to do that sort of thing. And then another thing you can try to do is sort of like the synthetic data idea is like, just search for inputs on which your AI system would do something bad. And that's sort of what adversarial training is. And then interpretability is just like, man, if you just understood how your system was reasoning, then maybe you could notice when it was going to do something bad. So it's sort of those are the sorts of things I would highlight as ways that you can try to tackle the sort of bad generalization problem. I should also skip the slide, in which case we're at takeaways, which I will just leave on the screen. But yes, cool. Thanks, everyone.
Thanks for joining, everyone. Our next talk is in 1 week on April 20th at 1700 UTC from Dr. Andrew Critch, who is a full-time research scientist at UC Berkeley at Stuart Russell Center for Human Compatible AI. His talk title is Open Source Game Theory, What AI and Decentralized Tech Need to Learn from Each Other. If you're watching on YouTube, please remember to hit the like and subscribe buttons and share this video. If you want the Zoom link to join future talks, you can join our mailing list in the footer at research.protocol.ai. Thanks for joining, everyone. We will see you next time.